In this video, we're going to talk a little bit about concurrency in programming languages, and in particular, Java's use of threads. Java has concurrency built in through threads, and I'm not going to explain what a thread is from first principles in this video, so I'm going to assume a little bit of background, but we'll say a few words here about what threads are. So a thread is like its own program. It has its own program counter, meaning it has an instruction that it's executing, and it has its own set of local variables and activation records. And a Java program, or any program written in any language with threads, may have multiple threads at the same time. So abstractly, we can think of threads as being a series of statements that are executed. Each one of these threads, again, has its own set of local variables. But the threads may refer to common data in the heap, so they could refer to the same heap data structures. And each thread is executing a particular instruction. So let's say that the threads are all here. We have 3 threads, 1, 2, and 3. And they're each at some instruction or some statement in the program. And then there is a scheduler. And at each step of execution, the scheduler will pick one thread to execute, and it'll execute one statement. And this is conceptual, meaning this isn't exactly the way it's usually implemented. And then it will repeat this loop. So it'll pick a thread, it'll execute one statement of that thread, and it'll just keep doing that over and over again. So we might, for example, the scheduler might pick thread 1 and execute this first statement. And then it might pick thread 2 and execute this statement. And then it might pick thread 3 and execute that statement. And then it might decide, well, to execute another statement of thread 2. And then it might execute several statements of thread 1. And then it might come back and execute a couple statements of thread 3. And then thread 2 might get to go again for a while, and so on. All right, so the threads execute in some order. And it's non-deterministic at each step of execution which thread will execute, how many of its instructions will be executed. And thus the threads may interleave, the instructions in the threads may interleave in a relatively, or in fact completely, arbitrary order. All right? Now, coming back to how this is done in Java, thread objects in Java all have class thread. So there's a special class that you have to inherit from in order to be a thread. And what you get when you inherit from the thread class is you will have start and stop methods for beginning and ending the thread. All right? And there's some other special properties of threads. And in particular, one thing that threads can do is to synchronize on objects. So a thread can acquire a lock on an object through the synchronized construct. And so if I say synchronized XE in Java, what that means is that the program will acquire a lock on X before it executes E. So the procedure here will be to lock X, then evaluate E, and then unlock X. All right, so it's a structured synchronization construct, and while it's executing the expression E, it will hold a lock on X. And this is the primary way, really almost the only way in Java, to get synchronization between multiple threads. So this is how one can control the set of interleavings, because while one thread is executing this particular block of code, no other thread can execute this block of code and also hold a lock on the same object X. Now, two threads could execute this same syntactic construct if they were locking, if their local variables X referred to different objects, but they're guaranteed not to interfere with each other, not to interleave if they try to lock the same object X. All right? Now, and then there's one shorthand in Java, which is used more commonly than this form of the synchronized construct, and that is that synchronization can be put on methods. We can say synchronized F, where this is a method definition. All right, and what this means is that when this method is called, that this object will be locked. So here, the object that's going to be locked is implicit, and when synchronize is attached to a method name or a method declaration, that always means that this parameter will be the synchronized or locked object. let's take a look at a simple example and think about what happens if we have two methods, one of which calls the method to of the class simple and one of which calls the method fro. So let's take a look at that. Let's say we have thread 1 and we have thread 2. And now thread 1 is going to invoke the method to, and thread 2 is going to invoke the method fro. All right, so one possibility here, let's say that, that 2 gets to run all the way to completion before fro executes anything. So then we'll have a equals 3 and b equals 4. Okay, and then fro will run and it will print out the string a equals 3, b equals 4. Okay, so that's a relatively simple, straightforward case. Another possibility is that thread 2 gets to run before thread 1 ever does anything. So thread 2 executes all of its instructions before thread 1 executes anything at all, in which case what will be printed? Well, the fro will print out a equals 1, b equals 2, all right? And 2 will then run and it'll set after this executes. So after fro finishes executing, it will then set a equal to 3 and b equal to 4. So that's another possibility, and both of those are fine. All right, but then there's some other odd possibilities, and let's take a look at one of those. What happens if the threads actually interleave in a non-trivial way? So let's consider the following possibility. Let's say that 2 executes the assignment a is equal to 3. And now fro executes the first part of the print. So it does the read of a and starts building up this output string. Okay, so it's going to print out here a is equal to 3. All right, and then now let's say that fro actually goes ahead and gets to run some more, and it also goes ahead and prints out the rest of this. Okay, so it actually does the second read of b. So then it will print b is equal to 2. All right, and then 1 will run the rest of the way through, excuse me, b is equal to 4. And so here we got an output that doesn't seem quite right. Here we were able to see an intermediate state where thread 1 had only executed partially. And so what came out over here in fro showed just a partial update of the variables a and b. So one had been written but not the other. And if we didn't want to do that, if we thought this was wrong, we would have to use synchronization in order to control that. So let's take a look then at using synchronization to try to prevent this from happening. And I'll tell you right up front that this piece of code or this attempt is incorrect and actually doesn't solve the problem at all, but it also illustrates probably the most common thread programming error that Java programmers make. And lots of people, including professional programmers, make this mistake, and lots of production Java programs have this particular mistake in them. So it's a very instructive example, I think. So let's take a look here. Let's assume we have the two threads again, the thread that's going to call to and the thread that's going to call fro. And let's say that in our heap there is only one object simple. And let's just call it S. So there's globally in the entire heap just one object S of the simple class. All right, so what is, let's say that thread 1 is going to go first. All right, and the first thing it's going to do, because it's a synchronized method, is it's going to lock this parameter of the call. And since there's only one object of the simple class, that has to be the object S. So it's going to lock S. All right, and that will prevent any other thread from acquiring the lock on S while thread 1 holds that lock. So then thread 1 could go ahead and execute the statement a equals 3. And now, though, we could have an interruption and thread 2 could get to run. And notice here that thread 2 doesn't check the lock. It goes ahead and executes this code over here in the fro method, but that's not synchronized. There's no synchronized keyword there. And so just the fact that somebody else holds the lock on the simple object doesn't prevent another method from accessing the fields or the data of that object if that other method doesn't itself check the lock. So if the other method is not synchronized, it will just go ahead and execute, ignoring the fact that another thread holds the lock on the object. So in this case, this can just run to completion, and we'll print out A equals 3, B equals 2. Okay, so we only see one of the two updates. And then the scheduler could come back in, let the other thread run, and it would run to completion and unlock the object at the end. And you can see here that this particular attempted fix has achieved nothing. Actually, all the possible interleavings of the two methods that existed without any synchronization still exist if only one of the two methods is synchronized. And the reason this error is common is because frequently people think, well, reads are okay. I can always read from things in parallel, and that won't cause any problems because I'm not altering any data. It's my writes that have to be synchronized. So if I'm going to write to fields of objects, well, that needs to be coordinated with other methods because writes are dangerous, but reads somehow don't interfere. And the point here is that if having only one method or only having one half of the accesses of two accesses to shared data be synchronized doesn't help, because synchronization only works if everybody is checking the lock. So both the reader and the writer need to check the lock in order to restrict the set of possible interleavings of these two methods. So what would be a correct way to do it? Well, is to put the synchronized keyword on both methods. And now it's not possible to have the interleaving we saw before. So now there's only two possible outputs. One, there's only two possible strings that could be printed. One is that A is equal to 1 and B is equal to 2. So in this case, the fro method executes before the to method. So that's fro before to. Okay, meaning all of fro before all of the to method. And the other possibility is A is equal to 3, B is equal to 4. All right, and that would be the to method executing in its entirety before the fro method. And those become the only two possible interleavings when both methods here are synchronized. I'm going to conclude this video by making a couple of other comments on Java's threads. So one property we would like is that even if there is no synchronization, a variable should only hold values that were actually written by some thread. So what do I mean by that? Let's say that we have two assignments. This is in thread 1, where we're assigning A the value 3.14, and then in thread 2, we're assigning A the value 2.78. And so after these assignments are done, after they've executed in some order, what do we expect? Well, we expect that A ends up being equal either to 3.14 or 2.78. All right. Now, what we don't want is for A to wind up being some other value. Okay. I mean, what if A turned out to be 3.78, for example? Okay, this would be bad. We don't want this, right? Because this value, 3.78, was never written by either thread. Okay, this value is somehow manufactured. And I chose 3.78 to kind of indicate what could potentially go wrong. If we somehow wound up with a mix of the bits or the pieces of the number from thread 1 and thread 2, if they were recombined in some strange way, then we could create a number that was assigned to A that didn't exist in either thread. Okay, it was never actually written in either thread. Now, Java does guarantee that the writes of values are atomic, meaning if I write to a value, if I assign a primitive type to something, that is going to happen atomically. It won't be interfered with by another assignment to the same memory location, except for floating point doubles. So this does not hold. Writes to doubles are not necessarily atomic. Now, why would that be? Well, a double is a floating point number, but it consumes twice the memory. That's why it's called a double. It consumes 2 words. Okay, and what that means is that if A here is a double, so let's assume that A is a double, that means that this write of 3.14 actually translates into 2 machine instructions. We have to write the high part of A equals something, and then the low part of A. So it'll be 2 machine instructions to write both of the words that represent A. You have to write the high half and the low half, okay, because there isn't a primitive double word write on most machines. And the same thing would happen in thread 2. This would get broken up into 2 assignments to the 2 halves of A. And then, just from what we discussed before, you can see that these could interleave in some way, and you might wind up with the unfortunate situation that the high half of the representation of A is written by thread 1, and the low half is written by thread 2, and then you could get a number like this, like something not exactly 3.78, but some mix of the bits from the write in thread 1 and the write in thread 2, and you would create what's called an out of thin air value. Okay, and clearly out of thin air values are bad. Okay, you do not want those. And Java guarantees, again, that the writes of almost all the primitive data types are going to be atomic, so you can't get out of thin air values. But for performance reasons, this is not the case for doubles. All right, so what it says in the manual is that as a concession to current hardware, they do not require that writes to doubles be atomic unless you, the programmer, go and mark the type as volatile. So you have to declare doubles to be volatile, and if you do that, then they're guaranteed to be atomic writes. Okay, so if you were writing Java programs using Java threads, and you're programming threads that read and write doubles concurrently, then you need to be careful to declare those double values volatile, at least currently. And this may change in the future, and I'm sure they would like to change it. But currently, you have to declare the doubles volatile to guarantee that the writes will be atomic. More generally, or actually somewhat separately, this is actually a separate point here, Java concurrency semantics are actually kind of hard to understand in detail, and this issue around out of thin air values is one aspect of this. There are several other aspects of it, and this is really not Java's fault. It turns out that concurrency semantics are hard, and actually this is kind of at the frontier of research. We don't really understand exactly what we want or what the right thing is to do to specify the behavior of languages in concurrent settings. And that's not to say that we don't understand anything. We do have some languages with perfectly good concurrency semantics, but in a language as full and rich of features as Java, there are a number of things that are not completely clear how they should be implemented on certain machines. And there's been a huge amount of work done on this problem specifically for Java. And actually, Java was the first mainstream language to have first-class threads in it, and to try to integrate that with all the other language features all the other modern language features that we like. And so it's not surprising, actually, that we've run into some trouble understanding how they're supposed to work in all situations. So this is one area of Java that I would say is still under debate. And while if you do relatively straightforward things with threads, everything will work fine. If you're doing, there are some areas of the language where if you try to use them with threads, you can get into a little bit of trouble. All right, so it certainly pays to try to understand Java concurrency and the threads if you're writing significant concurrent Java programs.